Welcome back to the second part of section 3.5. Just going to finish up a few more problems. You can see the natural log model and the common log model. They look very similar because they're both logs. Natural log is log base e, and common log is log base 10. So now, some examples of how we can use this. Now, on the Richter scale, the magnitude R of an earthquake with intensity I is equal to the log base 10 of I, the intensity, over I sub 0, which is the initial intensity, which is 1. The minimum intensity is used for comparison. Find the intensities per unit of area. So what we're going to be doing is we're going to be finding the intensity of the earthquake. We're going to be finding I. So R equals the log, we don't even need the 10, I over I sub 0. Keep in mind that I sub 0 equals 1. That's our initial intensity. So now 8.3 equals the log of I over 1. So 8.3 equals the log of I. So to undo that log, we're going to use our exponential. So 10 is the base. So 10 to the 8.3 equals I. Now, just to show you how big of a number that is, 10 to the 8.3, when we take that out of that notation, we raise 10 to the 8.3, we're going to get 1, 9, 9, 5, 2, 6. So when we put the commas in, you can really see how big of a number it is. It's 199 billion. 199 million. Oh, I can't think today. Sorry about that. 199 million. That's quite a bit. So you would expect that 7.7 would be pretty similar. So once again, R equals the log of the intensity over I sub 0. So 7.7 equals log of I over 1. So 10 to the 7.7 equals 10 to the log of I. So I equals 10 to the 7.7. So you expect that value to be pretty close to the other one because 7.7 and 8.3, they're not that far apart. But when we write it out, I equals you can see it went from almost 200 million to 50 million. That's quite a big difference. So that difference of 0.6 on the Richter scale was actually 4 times the intensity of the 7.7. Because if you have 200 million, just rounding, over 50 million, you're going to get 4. So it's 4 times more powerful. So 0.6 on the Richter scale is actually a 4 times more intense earthquake. I thought that was pretty interesting. It really shows you how that logarithmic scale works in that way. Now we have a growth model, and really it's just using this model. A logistic growth model. Y equals A over the quantity of 1 plus B times e to the negative rx. Y is the population, x is the time. So we have this model for number 5. So this is a pretty fitting question. So a college campus, about 5,000 students. Person returns with a contagious and long-lasting flu virus. So the spread of the virus, y equals 5,000 divided by 1 plus 4,999, e to the negative 0.8 t. So how many students are infected after 5 days? And it can show you how fast things can spread, especially in a college campus. So 5 days. So our t is going to be 5. So y equals 5,000 over 1 plus 4,999 e to the negative 0.8 times 5. So y equals. So when you do that calculation, you're going to get about 54.019. So about 54 students in only 5 days from that one student. So in 5 days, that one infected student became 54 infected students. Now, they say they'll cancel classes when 40% or more become infected. So 5,000 times 0.4 is 2,000. So once we reach 2,000 infected students, they cancel the classes. So that's what we want our value for y to be. Y equals, so 2,000 equals 5,000 over 1 plus 4999e to the negative 0.8t. We're solving for t for this one. So we can make this a proportion. Put the 2,000 over 1 and cross multiply. So you have 2,000 times 1 plus 4999e to the negative 0.8t equals 5,000. So to isolate, I'm going to divide both sides by 2,000. So we have 1 plus 4,999e to the negative 0.8t equals, and 5,000 divided by 2 is 2.5. Subtract the 1. 4,999e to the negative 0.8t equals 1.5. Then we divide both sides by 4,999. e to the negative 0.8t equals. Now I'm actually going to leave it as 1.5 divided by 4,999. I don't feel like dealing with the decimals right now, and I'm going to save all my rounding until the end. So to get rid of the e, we're going to take the natural log of both sides. So we get negative 0.8t equals the natural log of 1.5 divided by 4,999. And then we're going to divide both sides by negative 0.8. And we're going to type it into the calculator just like that. So t equals, and you're going to get about 10.13 days. So it'll take 10.3, we'll just put 10 days for them to shut down classes. That's how fast things can spread on a college campus, especially in the crowded dorms and things like that. Interesting fact, with all the mask wearing lately, common colds and flus have gone down significantly this year. So the masks work not only just for COVID, but they also work for regular other everyday types of things. Okay, that is it for chapter 3. Thank you, and I'll see you in the next video.